Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, it's my great pleasure to introduce Richard Jones to give a talk. He wrote the book on garbage collectors, and then 10 years later wrote the next book on garbage collectors. And I think he's going to talk about garbage collectors.
Yeah, you've kind of got what I do. Well done. Right, okay. So what I'm going to do today is talk about a couple of things that we've done in the context of on-the-fly garbage collection. First of all, before I forget, I have to give the credit for a lot of this work to Carl Ritson and Tomoharu Yugawa, who are a couple of really, really smart young researchers. So they probably take credit for most of the smart ideas. I'm responsible for the dumb slides or whatever. So this work has been done in the context of the MirrorGC project. What we've been trying to do is build a fully concurrent copying garbage collector. By fully concurrent, I mean that it never stops all of the threads at any one time. The most it ever does is stop one thread at a time, for example, to scan its routes. And we've done this work in the context of the Jikes RVM metacircular Java virtual machine. It's a Java virtual machine that's written almost entirely in Java, apart from a small core of C. And we've been running it on fairly standard multi-core hardware. So what I thought I'd do today is I'd give you a background on Concurrent GC. Anybody who knows a lot about Concurrent GC can have a little snooze for 15 minutes, but I thought it would be best to get everybody on the same page first. And then I was going to talk about an opportunity and an issue. And the issue we found was trying to process Java's reference types, because we started off with Jikes RVM, we ran our concurrent collector, and we got bugs. And we thought, hey, what's going on? And then so we looked at what Jikes had been doing, and then we looked at the specification of Java reference types, and we thought something needed to be done. The other thing we looked at was, and this is the opportunity, in I think June last year, Intel brought out the Haswell family of processors which provided transactional memory. So we rushed out and grabbed the best Intel Haswell processor we could get, only to find that it didn't provide the transactional memory. So we got sort of one slightly further down the sort of specification, and that did. So that. Thank you, Intel. That was annoying, but and we looked at various ways to exploit transactional memory to support GC. So a background, and as I say, for those of you who know lots about GC, I do apologize for trying to teach you to suck eggs or whatever. So broadly, I'm interested in tracing collection. There are two styles of tracing collector. Does this have a point? Yes, it does. We might do mark sweep collection, where you start from some route, you've got some graph of objects, and basically you walk over this graph of objects, and as you visit objects, you set some kind of mark bit, which might be in the object or it might be in another side table. And when you've finished, you then sweep the heap, and anything that hasn't got a mark, like these ones, are garbage, and you can throw them away. The problem with mark sweep collection is it's not moving, and so you can end up with fragmentation. You can end up with holes in the heap that although you might have a lot of them, none of them are big enough to admit any allocation requests that you might make in the future. So the other style is copying collection. And here we've got some graphs. So here maybe we've got a list with a pointer to the head and to the tail. And what the collector does is it walks over this, and as it visits each object, it copies it into another space. So we have a from space and a to space. And you're copying objects from space to to space and compacting them as you go. And the key thing to note here is that as I copy this object A, I have to leave a note in A's header of where I've moved it to. And this is important for when you've got sharing, because you want to preserve the topology in to space and from space. Otherwise, you get multiple copies of shared objects in 2-space, and that's a bad thing. It's a particularly bad thing if you've got a cycle, because then you'll get an infinite number of copies if you don't do something like that, and that's probably not a good idea. So, I mean, pretty broadly, those are the two styles of collection that almost every modern garbage collection algorithm works on. They do something like that. I mean, you can also have compaction where you try to slide objects down to the bottom of the heap, but I don't think people use that kind of sliding compaction. When they do compaction, often they do something like this, particularly because you've probably got multiple GC threads doing the work at the same time, so you want to give them each their own region in which they can compact things in. Anyway, that's not germane to this talk. So all of that's ancient stuff. What's new today is that we have lots of parallel hardware. It's really ubiquitous. So how are we going to deal with our collection? Well, the simplest and easiest way is we have lots of mutator threads running. These white bars meant to be mutator threads. Time is running along that way. And every so often we run out of memory, we stop the world, and we do a collection cycle. So here's cycle number 1. Finish that, start the world up again, all the mutators running, and stop the world again. That's obviously a very bad use of parallel hardware, and it leads to all the big pauses that everybody always complains about with garbage collected systems. I mean, there is an old joke, which I will, that there was people complained about the pauses in Emacs caused by garbage collection. And the garbage collector implementers, because we're an arrogant bunch, we thought the users were idiots, so we won't have any problems with our pauses. So they replaced the message saying garbage collection, saying waiting for NSF traffic, and then gave it to the users. And they all said it had improved performance wonderfully. So stop the world is one thing. Well, the obvious thing to do is, rather than just use one thread for doing collection, when we stop the world, we'll use all the hardware contexts we can. So we get as much parallelism as we can, make these pauses shorter. But you've still got pauses. So what can we do a bit better? Well, maybe we can do it incrementally. So every so often we probably have to stop the world to do some kind of synchronization. Typically what that means is maybe we scan the roots of all these threads so we know what's on all the stacks, and then maybe we let the mutators go again and ask them to do a bit of garbage collection work every so often until we finish, and then we repeat again. Or we can do it more concurrently. So again, we let the threads run, stop the world briefly, again, to scan all of their stacks at the same time, because that makes it much easier. And then we let a garbage collector thread run concurrently with the mutator threads. And we hope that this bar is short enough so that it completes before we run out of memory again. Yep.
So you seem to imply that the scanning typically doesn't take too much time compared to the rest of the stuff that happens.
Yes.
Okay.
Yes. Scanning is pretty short. I mean, yeah, because certainly in Java, the depths of stacks are usually quite shallow. Now, if you're working in a functional language with lots of recursion, you're going to get deeper stacks.
Well, I mean, but it's not just a stack. I mean, if you're working with linked list objects that are very fat and stuff like that, okay, you start from the stack, but you.
Oh yeah, but we deal with the linked list objects in sort of this part.
Oh, I see. So you just do the stacks.
We just do the stacks here.
Ah, that's
it's just so we know. It's very bright here. It's just. I should have brought my hat. It's just so we can snapshot the state, if you like. Yeah, because trouble with these pesky mutators, they keep on changing things, and it's a real nuisance. And this is what we've done, and what this talk is going to be about, or we can do the collection on the fly. And the idea here is, although you might pause an individual thread for a very short time to scan its stack, almost all of the collection work is done concurrently. So we're never pausing more than one thread at a time. And we can do that very quickly. Now, it's probably, it is possible to break down the scanning of stacks into even smaller quanta, but we haven't done that because it gets more complicated and nasty. Right. Now, as will be no surprise, once we start talking about all this parallelism, and in our case we have multiple collector threads, multiple mutator threads all running at the same time, you get issues of consistency and issues of synchronization. So it helps to abstract about higher than the level of sort of code to think about what's going on. And the way to do this, or a well-known way to do this, is what's called the Tricolour abstraction. And here we have the notion that every object conceptually has a colour, and there are lots of different ways that you might represent that colour. White objects are those that the garbage collector has not reached. And so by the end of the collection, anything the garbage collector has not reached is unreachable, and hence is garbage. Black are objects where the garbage collector has reached it, knows all about it, has scanned its fields, and the garbage collector does not need to go and revisit those objects. And the intermediate stage is grey, which the garbage collector knows about this object, but maybe hasn't finished scanning its fields, or maybe needs to come back and scan them again because they've been changed or something like that. And as I say, by the end of garbage collection, you hope that the world will have been divided into black objects and white objects, and there are no grey objects left. Because if there are grey objects left, you've got more work to do. And that proves to be a very powerful way of thinking about garbage collection. So here's the fundamental problem for any concurrent garbage collector. You can lose objects. So consider this scenario where a mutator is going to hide a reachable object from the garbage collector. So we started from some roots, maybe. The garbage collector's visited this object, knows all about it, knows what its fields are, gone and visited this one, knows all about it. And then the garbage collector pauses. And the mutator comes along and says, I will copy this pointer A, and I will install it into X. And then I will remove pointer A. And at this point, the garbage collector wakes up again, says, well, I've done the roots, I've done X. I need to go and have a look at Y. I'll go and have a look at Y. Oh, it's got no pointers in it, so I can mark that black, and I'm finished. And so I'm going to reclaim object Z. Wrong. That needs to be reclaimed. That needs to be preserved. So something's gone wrong there. Slightly more subtly, it can also do this in a more transitive way. So here we have a similar scenario. So we've got a state like this. Garbage collector has seen this object, knows all about it, knows all about P, knows Q is there but hasn't scanned its fields. And then it pauses, and at this point the mutator decides to copy C and install it in P. And it will delete some other pointer. Well, it could delete that one, or equally it could delete that one. Doesn't really matter which. But at that time, the garbage collector then wakes up and says, "Oh, I'll have a look at Q. It's got no fields in it, no pointers in it, so I'm finished." And so again, we have this object, which is reachable, but is going to be collected. And we don't want either of those things to happen. So how does that come about? Well, there are two conditions. I think these conditions are due to Paul Wilson from way back in 1992. I don't know of a succinct expression of this problem that predates this. So what he says is, this problem can happen if two things happen. First of all, a mutator is storing a pointer to a white object into a black one. And secondly, there is no route to that white object starting from a grey object passing through a chain of white objects. I mean, the black to white is fairly obvious. That came from those cartoons on the previous slide. The path issue is that if there is such a path starting from a grey object, we know we've got to go and deal with, the garbage collector knows it's got to go and deal with the grey object, and it will walk along those white objects, and it will eventually find this object that's cause a problem. So we need invariants to prevent either of those happening. And the invariants are, there's a strong invariant and a weak invariant. The strong invariant captures condition 1. It says there will be no point, we've got to make sure there are no pointers from black to white objects. So pointers like that are not allowed. And the second one, the weak invariant, which is an alternative, is to say if there is a pointer from a black to a white, then there's this chain of pointers starting from a grey object, going through white ones. Notice it can't go through a black one, because that would stop your trace. Because you say, oh, it's black, I finished. And I'm going to call that these two objects grey protected, because they're reachable from a grey object. And it doesn't matter which of these invariants we impose. Either invariant is sufficient to make our program correct. The choice of which invariant you wish to support is all about efficiency and implementation and so on. And we maintain those invariants with barriers. These are actions that the mutator performs that communicate with the garbage collector in some way. Typically, if you're in the Java world, you're writing references with a bytecode like put field. You make sure that your put field implementation, as well as writing that pointer, also does some communication with the garbage collector, like color the object. I mean, you could have an explicit color in the header of the object, or you could say, well, the way I'll make an object grey is that I will put it on a work queue of work to be done, and that's what you really do. And there are two kinds of barrier. Well, actually, there's 3. I'm not going to talk about read barriers, other than just to mention them. I'm mainly going to talk about barriers on write actions. We prefer barriers on write actions because write actions are much more rare than read actions. And we'd really like to avoid putting costs on reads because it's inefficient. So there's 2 kinds of barrier, one of which I call an insertion barrier, and one of which is a deletion barrier. Other terms are incremental update or snapshot at the beginning. I call them insertion and deletion because that's the barrier you do when you insert a pointer, that's the barrier you do when you delete a pointer. This is called snapshot at the beginning because effectively it takes a conceptual snapshot of the heap at the start of the collection. And anything that was live at the start of the collection will be live at the end, pretty much. So, I've talked about colors of objects, but a really nice piece of work by Pekka Perinen way back also extended the idea of colors to mutators. So you can have a black mutator and a grey mutator. Remember the idea of black and grey. Black used completely, the garbage collector is finished with it, grey needs to do some more work. We extend the same idea to the mutators. So a grey mutator is one in which its roots maybe have yet to be traced. We've got to yet scan the stacks, or maybe we need to go and scan the stacks again for some reason. But anyway, we've got to do more work on the stacks. And this means that the stacks may perfectly legally point to objects of any color, black, white, or grey. Black mutators, in the same way as if we say an object is black, we don't need to trace it. If a mutator is black, the garbage collector doesn't need to go and look at it again. And the sorts of things that a black mutator can point to depends on which of the invariants we're going to support. So if we're going to support the strong invariant, which is no black to white pointers, that means it can never point to a white object. We make sure that there are no white objects on the stack. If we're going to support the grey invariant, we say, well, this mutator can point to, this stack can hold references to white objects, but those white objects better be grey protected. In other words, there better be a path from a grey object through a chain of white objects to that object, and then we're safe. And to enforce those invariants, we can use 2 different kinds of barrier. So if we're working in the world of a grey mutator, we use an insertion barrier. And this is old hat. This is from Jikes. So here we have a black object and a white object. We want to write this pointer. So as we write that pointer, we've got to colour that object. And there are all sorts of subtleties about the order in which you do it, which is sort of counterintuitive, to be honest. If we're working in the world of a black mutator, there are several things we can do. We could have a read barrier which says we will make sure that whenever we load a reference onto the stack, we will make sure that we've coloured the object target first. But I don't want to talk about read barriers because they're expensive. So what we're interested in is a deletion barrier. So here we have a pointer from an object. That's meant to mean this object could be grey or white. Keynote didn't quite get the contrast as aggressive as I wanted it to be. So we're going to delete this pointer from a grey or white object. And when we do that, it means that the target we're going to say is grey. So that's why it's called a snapshot, because this object, we've deleted the pointer to it, but the collector is still going to preserve it. So it means that anything that was live at the beginning of our collection cycle is going to be live at the end, pretty much. So why are we interested in these two? I mean, clearly, this one looks better because it doesn't have so much floating garbage. This one is producing you all sorts of stuff. This looks like it's going to be garbage, but you're going to keep it around? How stupid. You've got loads of floating garbage. So why would we want to do that? And the answer really is all to do with termination. If we've got the grey mutator, that's the one that supported that. Here's our termination advance. Here's our termination loop. So we start off, we trace until there are no grey objects left, till our work lists are empty. And that means, but the trouble is, as we're doing that, these sneaky mutators, they might start loading references from our stack. The mutator might run ahead of the collector, grab a reference to a white object, install it on the stack, and delete the original reference to that white object. So the collector's not going to find it. So I think I shouldn't have said grey. I think I should have said white there. Anyway, the problem with that is that the stack of one of the mutators might hold a white object. So we've got to go and find that. So we have to scan each of the thread, shading any white objects found, putting them onto our work queue. And then if we did find any, we've got to go and trace them again. And once we've done that, we're pretty much back to where we were there. So you've got to go around the loop again. And you do this ad nauseam until you've not found any grey objects. And you could write an adversary program that would make that loop forever. So how do you stop it looping forever? Well, maybe you make the system run out of memory, so it has to stop all the user threads. Or maybe the garbage collector says, I'm bored with you mutator guys, I'm going to block you all until I finish doing that. In contrast, here is press wrong button. Here is the termination process of a black mutator. It just traces, does a normal trace until there are no grey objects, and it stops. We are finished. Why is that safe? Well, because we have the Tricolour referent. So the mutator can only hold black references. We've done all this tracing. There are no grey objects left. If there are no grey objects, that means there are no white objects that are reachable from grey objects. And because the mutator is black, there's no need to rescan it. Simple. So the weak invariant gives us this very nice termination property. And when I get to talk about how we processed Java's reference types, I'll show you how we did it with both a grey mutator and a black mutator, and I'll show you the differences. So I need to give you a bit of context about the collector we've been building. We've we've been working with a collector called Sapphire, which is quite old now. It's by Rick Hudson and Elliot Moss. We originally decided to work with Sapphire because we have a new algorithm and we wanted something to compare it against. So we were comparing apples with apples. So we thought, oh, we'll build Sapphire. That won't take long. 2 years later, we finally got it to be correct and the bugs out of it. So how does Sapphire work? Well, it's on the fly. It never stops more than one thread at a time. It uses copy and collection. The nice thing about copy and collection is it gives you very fast allocation. You just need to bump a pointer to allocate a new object. It eliminates fragmentation. And the subtle part about Sapphire is it's replicating, so it has it maintains two copies, a copy in from space and a copy in to space while it's doing the collection. But for synchronization, it makes sure that the GC pays most of the costs of synchronization. So it's not putting much of an overhead. It does put a little bit of an overhead, but not putting much of an overhead on the Mutator. We completely re-engineered Sapphire in Jikes RVM, and Intel was very kind to give us a license to do so. Jikes is a research virtual machine. It's largely written in Java. The great benefit of it is it's, quote, easy to replace components, like you switch different garbage collectors. And it is pretty easy. It's easier than any other system I've worked with, but it's not trivial. So this is how Sapphire works. It operates like all concurrent GCs in a number of phases. So to start with, here we are. We've only got a from space. Here's the Mutator. It's reading and writing from objects in from space. We've got a couple of objects which point to each other. We then decide we've got to do it at GC. So the first is the mark phase. And the way that Sapphire does its mark phase is it traces concurrently all the objects in the heap and allocates what we call a shell, an empty region of memory ready to put the data from space in. And it adds to the header of each of these from space objects a forwarding pointer telling you where the replica is, so you can find it later. Mutator's still reading and writing to from space. The next step is to do copying. So the garbage collector is responsible for doing all the copying. So it will take this object and copy the contents of that object into here. It has to do what we called a semantic copy, for want of a better word. In other words, we make sure that this is a pointer to something in from space, but we make sure that we replace it with a pointer to something in to space. So we've only got 2 space pointers in here, which means when you do this copy, you've got to do some lookup. You've got to follow that pointer, say, where is your replica? Oh, it's over there, right? Thanks. That's what I'll write. During this time, the Mutator is reading from space and writing to from space. But you've got the situation where suppose the garbage collector copies all this data over here, makes a proper copy of it, and then the Mutator changes something in there. Well, if it's done that, that value needs to be changed in there as well. And the only person who can do it is the Mutator. So we have the Mutator do a double write. How can we make sure that this is consistent? Because you think, well, okay, maybe you've got a race between the GC trying to write a value in here and the Mutator trying to write a value in here. And the answer is Sapphire forces the collector to use compare and swap operations to do those updates. And I'll show you the pseudocode for that in a minute. When we have copied it, the collector's copied everything to space, we've now got to start to flip. And in the flip phase, the Mutator is now reading from to space, but again, it's having to write to both. And the reason for this is our epochs between one phase and another are ragged. It's possible that one collector might be in one phase while another one's advanced to the next phase, because we don't want to stop them everything and force them all to transition atomically. So we have all this. I mean, I put the 1, 2, 3, 4, 5. There's a lot more phases than 5 because it takes several steps to transition from one phase to another. And by the end, we've finished, we've done everything, all the mutators are pointing at, all their stacks are pointing at things in 2 space, and so we can throw away everything in from space. Is that reasonably clear? Yeah? Happy to take any questions. I mean, do ask questions as I go. Right, that is the background. Let's get to the meat of the talk. Yeah.
Is that meant to be sort of, as one could imagine, the simplest on-the-fly GC? Or no?
The simplest on-the-fly GC will be a non-moving one. Something like just a concurrent mark sweep, because there all you need to do is decide which of those barriers that I was talking about you're going to implement. And there the difficulty is which termination algorithm do you want? No, we've gone out of our way to make it hard by being fully on the fly and by copying. So, yeah.
No generations.
We haven't got generations. It'd be very interesting, I think, to put generations in here, but hey, one step at a time. Yeah. I suppose if I was if I really wanted to defend this, I would say, well, what do generations do for you? They give you small pause times. We don't have it. We don't pause. So Java reference types. If you're familiar with Java weak references, you'll know what these are. But if you're not, let me say something briefly. So there are 4 kinds of reference in Java. There's the normal reference that we all do when we say new object, and that's a strong reference. But there are also soft references, which might be used for building caches that the GC can reclaim when it's under memory pressure. There are weak references that might be used for canonicalized mappings that don't prevent the garbage collector from reclaiming their keys or values. And there are phantom references, which are kind of weird, but can be used for pre-mortem cleanup actions in a way that's more flexible than using a finalizer, say. And I can point you to, if you're interested, I can point you to a very good tutorial on that. I mean, I'll let you have the slides and people can have a look. It's put in the notes. There are weak references don't have many methods, but one method that they have that is interesting, i.e. this is the one that we have to deal with, is a method called get. So here we have a reference, an object of some reference type, and it has a weak reference to a normal object. And you can call get on it. So if you've got a soft reference, when you call get on it, that will return you so I'm going to call soft reference.get on this object, and it'll give me a strong reference to the target. Or if the GC has decided to clear this reference, and the GC can decide at any time to clear that reference, it will return null. Similarly for weak reference, pressing the wrong buttons. Similarly for weak references, phantom references, whenever you call get, you get null. So there's a sort of marker there to let you know the GC reclaimed something. You can go and deal with it. That's why I say go and read the tutorial. I have never written any code with phantom references. Has anyone written code with phantom references? I don't know anyone who's written code with phantom references, but the tutorial does provide a fairly convincing rationale for why they might be useful. Now, the key thing to take home about get is, and this is particularly true if you've got a concurrent and on-the-fly system, your collector has gone and traced everything, i.e. it's traced all the strong references. It has decided which objects are live and which objects are dead, and then some mutator calls get, and suddenly an object that was dead is now live because you've got a strong reference to it. And if you ignore that, things go wrong. And certainly, it was the case that in Jikes RVM, before we fixed it, exactly that happened. Things went wrong. Why hadn't it been exposed before? Because nobody had stressed Jikes RVM with as much concurrency as we were stressing it with, I suspect. So garbage collectors are really interested in reachability. They're following pointers and trying to find objects which are reachable. So the Java Lang reference package defines reachability, and it's the only place you find the definition of reachability. So, first of all, you think, well, we found this problem in Jikes, we need to fix it. So we got out the Java specification, looked in the index for the word reference type, it wasn't there. So we then looked at the Java Lang reference package. Actually, there was a reference to the Java Lang reference package. So it's defined in there, and it says that there are 4 types of reachability. Something could be strongly reachable if you can reach it without traversing any reference objects. This is what you'd normally expect. This is normal GC stuff. And in this case, the garbage collector will not reclaim these. Objects might be softly reachable, which means they're not strongly reachable, but they can be reached by traversing a soft reference. And the GC may reclaim these. There's a strong hint given to the implementer if these soft references have been created recently or used recently, might be a good idea to keep them because somebody's using it to build a cache, and they'd probably be a bit upset if you threw the cache away as soon as they created it. There are weak something might be weakly reachable if it's neither strongly nor softly reachable, but you can reach it by traversing a soft reference, and the GC will reclaim this. And then there are phantom references, which are neither strongly, softly, nor weakly reachable, but have been finalized, and some reference refers to it. Now, one of the difficulties for implementation is that clearing reference types has an atomicity requirement. So imagine we have this picture here. We have, suppose this is a weak or a soft reference, and here we've got another weak or soft reference, and these are a bunch of normal objects. So if we were to call get on something, we get a race between the mutator and the collector. So the mutator is trying to make a strong reference of this object, which a GC would like to reclaim because it's not strongly reachable. So we've got a race. And the rules are, to avoid that if the GC decides to reclaim a softly reachable target, ditto weakly or whatever, you've got to not only remove all soft references to this object O, because we decide this is only softly reachable, and we'd like to get rid of it. So you've got to remove all these references, but we've also got to remove references like this, which might point through a chain of normal strong references to this object. And you've got to do that for all of these references at the same time. Or at least make the mutators believe it's happened atomically. And this is clearly a challenge for working with on the fly. So at last I come to what we've done. So we looked at the specification, and the specification says an object is softly reachable if it's not strongly reachable but can be traversed by a soft reference. It's kind of a vague definition, and this is probably what you'd expect from seeing definitions written in package documentation in English. I mean, particularly it doesn't specify how many soft references we can traverse, and it doesn't specify that there should be no weak or phantom references in that chain, and ditto for the other definitions, the other reference types. So what we did was we formalized this and corrected. The formalize, any formal method, but this is trivial formalizer. It's not very difficult. So we have a set of relations between objects. These are the representing references, strong, soft, weak, and phantom references. We have a transitive closure of those, so we can then say the set of strongly reachable objects is a transitive closure starting from the roots under the strong reference relation. We then can similarly define what our softly reachable, weakly reachable, and phantom reachable objects are. And I think there are no surprises there. It's really what you'd expect. And we can state what it means to clear references. So this, I think, is where we do make it clear what the specification in the Java Lang reference package should have said. So we say that if we're going to reclaim an object O, then the soft references we have to clear are all of these, and it's all of the ones that might reach O by following one or more strong references. And similarly for weak to clear. Notice phantom references always return null, so it doesn't matter. So, okay, we've done that. It was quite straightforward. Does it really matter? Does anybody use these funny references? To my surprise, they're used a lot. I expected them to be used, but I didn't expect them to be used as much as they are. So here are a bunch of benchmarks taken from Jikes RVM, and what we're measuring here, this is time, so program starts here, program finishes here, and we're measuring the number of calls to get in millions over that period, and very common as the JVM starts up. Lots of reference types used. They seem to be used again right at the end. We suspect that might be the harness. But some benchmarks, like Zelan, LU Search, use them heavily. Jython, which is an implementation of Python in Java, uses them very heavily indeed. So clearly there's something we have to deal with. So there are three options. We could stop the world. We could block any mutator that calls get, which has been done before, or we could process objects on the fly, never blocking, and that's what we chose to do. So here's we modified the GC state. So we're in a normal state. We start tracing, happily tracing away, and then the garbage collector wants to finish tracing and switch to the stage where it's going to do clearing, but the mutator might call get, and that's going to force the collector to repeat. So there's a race between calling get and the garbage collector finishing, so we need to deal with that, make sure that that happens atomically, whereas all these other transitions, as I said before, are fairly ragged. I'm not going to talk about the code in great detail, but here's the code for the collector and the barrier. The key point is that the collector tries to atomically change the state from tracing to cleaning, and the mutator tries, when it's found some reference that was white, it's changed to change it from tracing to repeat to make us go round again. And because it's insertion-barrier, we go round and round and round, just as I said before when we tried to terminate. We also implemented, and the problem with that, it gives us no guarantee of termination. We model checked this algorithm with Spin, and Spin also told us this is not giving you any guarantees of termination. However, if we use a deletion-barrier code, we've got the same sort of thing. Mutators trying to change from tracing to cleaning, but our barrier code this time, again, it's trying to make you repeat, but in the same way as when we deleted pointers, we colored the target here. And this does give us a guarantee of progress, and we terminate. So what's the result of all this? Here are a bunch of benchmarks. Here, these show the blocking method. So either we do stop the world, or we do the method that blocks by taking a lock on an individual collector.
On the last slide, so I know this is probably very unlikely, but when you colour it grey after you've set it to repeat, could the garbage collector go and completely finish tracing again before you colour it grey?
You think there's a race in here, do you?
Yeah. I think it's probably unlikely to trace a whole of memory before you get to it.
I do hope it's not. We did model check this, and I do hope the pseudocode reflects what we put in the real code. Okay. I believe this is correct, but I can entirely see your point. I think the answer is no, because we have a handshake in there. So I think that's what gets me out of jail there. But it doesn't. I mean, if I put my faith in the spin model checker for the bounded model checking, right? Okay. So as I said, stop the world or the lock based, and you can see these are histograms showing you pause times with three millisecond buckets. You can see there are pauses, and some of them can be a considerable number of milliseconds, given how long we would expect maybe something. I mean, someone mentioned generational collection. You'd expect a good generational collector to have pauses less than some of those. So here, on the right-hand side, I'll show our results for we're using our on-the-fly mechanism. On the left, again, the ones we had before. And this is the length of the entire phase for reference processing. So in the case of the lock, it's not how long a mutator was blocked for, it's from the start of the reference processing phase to the end, which might be different. And the other thing to note is these scales are logarithmic. So mostly all of these, they mostly finish quite quickly. Notice some of them, LU search, if I use the insertion barrier, it takes a long time, and it has to retry. In fact, it retried 62 times. But the key thing is the mutators kept running. And what was the effect on the overall execution time? Are just looking at the on-the-fly with the deletion barriers and the lock with the deletion barriers, they didn't have a substantial effect on overall execution time, and indeed, processing on the fly was often faster, or caused the system to finish faster than if we'd done it with stopping the world or locks. So, punchline is that it works. Now, I'll move on quickly because I appreciate time is passing. Right. The other thing we looked at was transactional memory. So the issue for as I guess is fairly obvious from now for doing concurrent GC is consistency, because there are races. But transactional memory is widely touted to be an efficient solution to the problem of writing concurrent software. I'm sure you all know how transactional memory works, but it allows you to execute a sequence of instructions, and if no other thread makes some kind of conflicting access, then your transaction commits, otherwise it aborts. And in June, Intel brought their Haswell architecture out, which provided this restricted version of transactional memory. It's got a very simple programming model. You start a transaction with xbegin, and you commit with xend. And the processor maintains these read and write sets at a cache line granularity. So it's tracking things at cache line granularity. Obviously, there's a limit to how big these read and write sets are, but it turns out to be quite big. If there's an abort, you need some kind of fallback handler, and Haswell will tell you what the cause of the abort was. So my colleague Carl measured this straight away. If you want to look at a detailed paper on the performance of Haswell, I recommend this one. And we found that typically the cost of setting up and tearing down a transaction was about the same as doing 3 compare and swap operations. We also found there's a penalty of reads within a transaction, but not on writes. And the reason for that is, we think, because effectively there's a penalty on writes anyway because of cache coherency. We could deal with transactions of sizes up to 16 kilobytes, which is about the size of the L1 data cache. And abort was expensive, as you might guess. So, going back to Sapphire, remember this slide where we got the mutator updating from space and to space in the GC copying. I mean, my next slide says, what could possibly go wrong? And the answer is you could get things out of order or something. I guess it's fairly obvious. So I promised you the code for the read barrier. Now, the original version done by Hodson Moss used compare and swap. So our read barrier is something like this. We do a simple read from to space, a simple read from space. We compare them. If they're different, we do a compare and swap, trying to write the value, and then we restart in case the mutator's messed with us again. If they are the same, we're finished and we're done, because then that means it's up to the mutator to make sure that the two versions are in sync. Obviously, using compare and swaps for all these copies is expensive. So we can do it with a transaction, and it's very simple. We just load the value from two-space and write it load from space and write it into two-space. Actually, it's a little bit more complicated than that, because you've got to do some work to set the transaction up. You've also got to deal with the case of transactions that might abort. And also the other thing is our copying. Remember, it was semantic. We were reading a value out of from space and trying to replace it with the equivalent value in two space. So there's a certain amount of lookup to do. So there's a lot of translation activity. So we then try to use Haswell to do this using hardware transactions, and the key thing to get this to work fast is we want to amortize the cost of setting up a transaction. We don't want a transaction to replace a single CAS. So instead, we would like it either to replace all of the copies for that object, or maybe all of the copies for a large number of objects. So we can make our transactions as big as possible. And there are two ways we can do this. We can either do it in line, or we can do it with a bit more cunning and planning. So the inline copying, we say we start a transaction, and then we add objects to the transaction as the trace finds them, and when we decide the transaction is big enough, we commit it. The problem with that method is that because you're having to do all this translational activity, you're putting too much stuff into your read and write sets. You're not just putting the things you really want, which is the right of that slot. You're putting lots of other stuff in as well. So the alternative is to do it in a planned way. And here the idea is that you want to remove all this scanning traffic and translation traffic from the transaction. So instead, we start putting objects that we're going to copy into a to-be-copied list. When we decide that list is big enough, then we start the transaction, copy the objects, and commit. So we get much smaller read and write sets, so we can do more useful work in the transaction. So that's hardware transactions. We also tried doing it in software as well. So here the idea was we copy an object, and then we verify that the copy is still correct. So the copying is done without it, using a compare and swap. We then verify the from space and to space against each other, and we also have to have a buffer because we've done all this translation. If that comparison fails, we fell back to compare and swap. We fell back to compare and swap with hardware transactions as well, I should say. So let me show you some results. And the results are for the original method using compare and swap, hardware transactions when we just copied one object at a time, or when we were copying 256 bytes worth of objects at a time, software, and we also did an unsafe, copy without synchronization. Now this is just so we could see what the bottom line was. And we did it and these pictures are from the Capo Eclipse. So here we are. This is the raw copying speed with the mutator stop. So it's not what would you want to use for a real concurrent collector, but just to see what's the baseline. So as you'd expect, doing it the unsafe way is the fastest, and doing it with compare and swap is the slowest. But we get a pretty decent speed up using either hardware transactions or software transactions. And you can see that the software transactions are pretty much the same performance as we get with using hardware transactions. Why is this? Well, the real reason is because our consistency guarantees are quite relaxed. We only need to be consistent eventually, at the time we've finished collection. If there's some inconsistency in between, that doesn't matter now. So that's not a general transaction or solution. We looked at what happened if we vary the size of the transactions, and if we did it inline, after we got to about 256 bytes, the performance fell off dramatically. But if we did it in the planned way, we maintained our copy speed as we increased the size of the transactions. If we did it for real, this is with the mutators running. So now we can't use the unsafe version. These are the results we got. Again, using compare and swap is pretty slow, but using any of our transactional methods, hardware or software, we get a pretty decent speed up, about 48 to 101% of the rate of copying. So we were encouraged by that, so we thought, hey, let's go and apply transactions elsewhere. And we did an audit of all the other collectors and looked at the fundamental mechanisms. And there are two other fundamental mechanisms, really. One is, can we do parallel copying in a stop-the-world collector? So you've got lots of GC threads trying to collect at the same time. And here, you want to make sure you only copy an object once, so you don't get a divergent trace. And we also looked at bitmap marking. Instead of setting a bit in the header of an object, which we could do with an ordinary write, because it doesn't matter if two threads do it in a different order. If they both write one, you've still got one. Looked at doing it in a bitmap. So here you've got a bitmap with one bit for each object in the heap. And here, if two objects try to write to the same word and changing different bits, you need to use synchronized operations, because otherwise you might miss one. The answer is it didn't work. It didn't give us any kind of benefit, and that was largely because, well, there are several reasons. I think it was because the overhead of setting this up to do multiple operations at once, because we didn't want to just replace one mark with a transaction. All this overhead of setting up multiple ones outweighed the benefit. It might, of course, be that Jikes was just so well engineered for doing it the way it does it that we couldn't beat that. Or it might be that the architecture of Jikes, which we tried to meddle with as little possible, was too complicated and provided too much overhead. So I can see Matthew looking at his watch. Last slide. So we found we could gain performance with transactions if we had sufficient and concise work. So sufficient means we've got enough work done in the transaction to amortize the cost of setting it up. And concise means taking as much work out of that transaction as possible. And I guess the interesting punchline is that using a portable method with software transactions gave us just as much benefit as using hardware transactions. So we don't need Intel after all. Okay.
So just time for a few short questions.
Yep.
Did the version that uses transactions leave racy reads in for performance?
Did it, sorry, use?
Did it still have racy reads for improved performance in the barriers?
I think so. You'd have to ask Carl, who implemented it, but I think it did, yeah. I mean, really, we didn't do a lot more than what I showed you on the slides. You know, we were careful to take stuff out of the transaction that we could, but apart from that,
wherever there were logs before, you put transactions, but didn't do any other.
Sorry, we only did it for the collectors. No locks. Yeah, we're not replacing locks. We're replacing these sequence of compare and swap operations that do the copying. It's entirely possible that there are other things that are interesting. We could maybe use transactions to replace locks in the system, where there are locks. Or maybe we could start from scratch and say, how could I build a collector that just used transactions? Really start from a blank sheet of paper. But that's quite tricky. I mean, we've thought about it a bit, but it's not clear how to do that. I mean, I think it's an interesting challenge.
Only the CAS predicted copy.
Yeah, that's what we did. And you could say, well, look at the Hudson and Moss's implementation. Why on earth would they want to use CAS for copying? What a dumb idea. Well, it works, and it takes a load off the mutator. Yep.
So when you introduced the problem with references, I was expecting you to say that you're going to use transactional to solve that.
No,
So would that be crazy? I haven't got my head around it yet. Because you want to atomically clear all the references at once.
Yeah. Yeah. I think the reason we didn't do that is it's dealing with copying. You can put a clear bound on where the transaction starts and where a transaction finishes, and it's quite limited. If you start doing it with reference types, it's in a sense the amount of work that might be done and the amount of work that goes into read and write sets, because you've got everything, all your threads running, gets very, very, very much larger. And so it's difficult to see how you would do that. So we didn't. I mean, maybe there's a way to do it, but it's not obvious to me that there is.
How much mutator races do you tolerate?
Sorry?
How much intermutator races do you tolerate, especially in the copying phase?
Right,
You
okay.
have Java code that's correct with respect to the Java memory model, but not much more.
Right. So if you read the original Hudson and Moss paper, it says Sapphire works properly for data race-free programs. And then it sort of flaps its hands about when it talks about volatiles. Well, what we did was we said, well, okay, volatiles are tricky. Let's see how often they're used. So we measured all these benchmarks and found out how often volatiles were actually, how many objects had volatiles in them. And the answer is, for these benchmarks, volatiles weren't used much. So we kind of passed on that by putting all objects that had a volatile field into a separate non-moving space. Jikes has many spaces. It has a copying space, it has a large object space, it has a code space, it has an immortal space, it has a non-moving space. So we said, well, there aren't many objects with volatile fields. We'll put those objects into the non-moving space. Tick. Now, I think that's a solution that works very well for these benchmarks. But you might say to me, hey, the future is massive concurrency. We're going to be using volatiles all the time. That solution won't work. Maybe.
One more.
What you formalized in terms of the strong and weak references and their transitive closure, do you think that should become part of the Java language specification someday?
Given that references are so intimately tied into the language, I think this is a general question. I mean, I talked to Scott Owens, who used to be here, and does something belong in a language specification? Does it belong in a library? Where does it belong? It's an interesting question, which I pass to theoreticians. But it certainly struck me as odd that something that is a core part of effectively the language is pushed to this rather informal definition in a package. Does Oracle take as much care with writing its text in the Java doc for packages as maybe Guy Skill and co do in the Java language specification? I don't know. I know how much most engineers enjoy writing documentation and keeping it up to date.
Okay, let's thank Richard again for a wonderful talk.